This is the presentation of the work entitled Test Case Generation of Actor Systems by Miguel Gómez Zamalloa in a joint work with Elvira Alberta and Puri Arenas. Okay, now let me start by giving an introduction. Well, it is well known that concurrency in programming is gaining a lot of importance, and it is also well known that there are additional hazards in concurrent programs which are not present in sequential programs like data races, deadlocks, and so on. And therefore, well, software validation and verification techniques used especially in this context. And the big problem in all these approaches is going to be the path explosion problem, because, well, in order to reveal a hidden error, then one has to take into account all non-deterministic interleavings of processes. And the big problem is that an exhaustive exploration is not going to be a feasible choice, and therefore the challenge is in avoiding as much as possible redundant state exploration or redundant exploration of paths. And well, there has been a lot of work proposing different algorithms and different extensions, well, based on the same ideas, all of them falling in the category of partial order reduction techniques. On the other hand, thread-based concurrency has shown to be very error-prone and very difficult to debug and analyze. And, well, a very good choice is the actors-based concurrency model, which is becoming very popular in languages like Erlang, Scala, and also in Java libraries for actors. Well, basically, the idea of this actors-based concurrency model is that each actor is going to be the concurrency unit. There is not going to be shared memory among different actors, but only shared memory internal to each actor. And therefore, information among the different actors is only exchanged by means of sending messages or by making asynchronous method calls. And also a very important property of this well, kind of concurrency model is that task scheduling is non-preemptive. Therefore, a task cannot be interrupted while it is executing. So thanks to these properties, the actors-based concurrency model is going to alleviate the path explosion problem, but still we will have an exponential growth on the number of states that needs to be taken into account, so it is not going to be sufficient. Now, this work is about automatic test case generation, and while one of the standard approaches to this problem is to do symbolic execution, which is what we do in our approach. So basically, in symbolic execution, an execution is performed with symbolic values or with constrained variables, and therefore there will be non-determinism due to branching instructions involving unknown data or aliasing of references to account for different heap shapes or the possibility of throwing or not exceptions, or in the context of concurrent programs we also have to consider the well, non-deterministic interleavings of processes as well. As a result of this symbolic execution for each path which is going to be generated, then we get a path condition or an equivalence class of inputs, so that if we pick an input satisfying this path condition, then it is going to be guaranteed that the execution of this program with this input is going to follow this path. So this can be used as the basis for test case generation, and we will get by construction a set of test cases which satisfy the path coverage criterion. Of course, well, we need to set some termination criterion to ensure finiteness of the process, and then with this criterion we will have a methodology to generate test cases automatically. And well, it is worth mentioning that in this context partial order reduction techniques are going to be even more crucial, because we have the other levels of non-determinism. And it is also worth mentioning that this symbolic execution technique has many applications like verification and symbolic debugging, and that the techniques that we have proposed in this paper are also applicable in these other contexts. Now, the contributions of this work are the following. So firstly, we have formalized a symbolic execution calculus for actor systems. Secondly, we have provided the extensions that are necessary to apply to the context of symbolic execution the state-of-the-art partial order reduction techniques. Then we have proposed new termination and coverage criteria for actor systems, and finally we have implemented and evaluated within the APET test case generation tool all the proposed techniques. Now let me go into the details of the path explosion problem. So basically the thing is, as I said before, we have to account for all possible orderings among different tasks. And well, we can distinguish two different levels of non-determinism, the level of the actor selection, the level of task selection. And the challenge is going to avoid redundant computations, in the sense that are computations that are going to expose the same behavior of the program. And now the theory of partial order reduction is the following. So given two tasks executed in the same actor, or in other words, two tasks accessing the same shared memory, then executions with the same ordering among these tasks or between these tasks are going to be equivalent, and therefore if we can find different executions with the same partial order of events, internally in the different actors, then these executions can be considered as redundant. So in this example, we can see that among these 6 executions, there are only 2 different partial orders. The one in which object O1 executes T1 and then T2, and the one in which object O1 or actor O1 executes T2 and then T1. That is to say, these two, or for instance, these 2 executions could be considered as the only 2 executions to be considered, and therefore we will be avoiding the generation of the other 4 paths. Now, the state-of-the-art algorithm for partial order reduction is called dynamic partial order reduction, and it was originally proposed by Flanagan and Godefroy and later adapted and improved for actors by Gul-Aga and colleagues. And well, the basic idea behind these algorithms is that each state maintains a so-called backtrack set, which is going to be dynamically updated with the actors that need to be explored. So basically, let me give you the intuition using a very simple example. So let us have a state with objects or actors OB and OB prime, and these tasks T1 and T prime. So at the beginning, we have to make an arbitrary selection of an actor. Then we start with OB, and then we execute T1. Now we only have in state T prime, so we execute T prime. And now let us suppose that T prime is producing a new task T2 on actor OB, because it is synchronously calling a task on this actor or object. And at this point, we are figuring out that this execution is exercising the partial order where T1 is executed before T2. But this means that we should think about the possibility of generating a different execution where T2 is selected before T1. And for this to happen, the only possibility is to backtrack at the initial state. And therefore, we will be adding this OB prime to this backtrack set. We will backtrack, and then we will be selecting T prime first, therefore producing T2. And at this point, we will have in OB both tasks, T1 and T2, so that we can try both orderings. Now, a very important observation that we made in previous work is that the effectiveness of dynamic partial order reduction highly depends on this arbitrary selection ordering. And the idea of this improvement is that we should select first what we call stable actors. So basically, an actor is stable if it does not receive any task before it is selected again. And the bottom line of this is that if we select a stable actor, then the backtrack set will remain empty, and therefore we'll be avoiding exploring redundant computations. So we will kind of give an optimal selection strategy. So in this previous work, we provided an analysis which computes a sufficient condition for actor stability. And the intuition, basically, in the same example, is the following. So in this initial state, when we have to observe that since T prime is calling OB.T2, then that means that object or actor OB is not stable, but object OB prime, it is stable because it is not receiving any other task. Therefore, at this point, we should start by selecting object OB prime. If we make this selection, then we will go directly to this part of the tree, avoiding the generation of this shaded part of the tree, and therefore, in this example, producing the optimal exploration of interleavings. And in this work, we have extended this technique to the context of symbolic execution. Well, it is important to observe that it is not always possible finding stable actor, either because the analysis loses precision at some point, or because actually there is not a stable actor. But in our experimental evaluation with well, a number of benchmarks, we have well, observed that only in one of them we have the situation that we are not finding stable actor. In other words, I mean, in 99% of the states, which are actually millions of states, stable actor is found, and that, well, empirically demonstrates that our actor selection is quite effective in practice, and also we have measured that it has no significant overhead. Now, also in previous work, we have shown that it's possible to further reduce redundant state exploration based on this idea. So the idea is to try to detect dynamically while the exploration is being done, to detect well, situations where two tasks which are independent in the sense that they don't access the same memory are executed consecutively. And the idea is that if T and T prime are independent in this sense, then it is enough to consider only one consecutive interleaving between them. Therefore, well, in this work, we have also studied the extensions necessary to apply this idea to the context of symbolic execution, and therefore to detect these consecutive independent tasks are pruned during symbolic execution. And again, the experimental results demonstrate well, a huge impact in this reduction, especially in symbolic execution. There are huge reductions in most examples, in many cases, 1 and even 2 orders of magnitude. Okay, now let me outline the other main contribution of this work, which is the definition of new termination and coverage criteria, which are going to be required to ensure the finiteness of and termination of the symbolic execution, and also guarantee that the test cases provide the desired degree of code coverage. So, well, the observation is that the very well-known loop K coverage is not sufficient for ensuring termination of, well, in general, concurrent programs and in particular actor systems. And therefore we'll have to propose two additional levels of well, termination criterion. One is the task level coverage and termination criterion, and the other one is the actor number coverage and termination criterion. Okay, so firstly, about the task level coverage criteria. So basically the idea is that we have to limit the number of task switches that are allowed in an actor or for each actor. So to illustrate this, let me consider the symbolic execution of the following very simple method. This method choose. So basically, depending on the values of these two arguments, it selects whether to compute P by making this asynchronous method call over this object or actor, or computing Q by means of this other asynchronous method call. In the case of P, which is the one that we will actually consider, then we are kind of computing a factorial by means of generating new tasks on the same object, new tasks in which we are computing the factorial with an argument which is decremented. So basically the symbolic execution tree will, well, firstly consider this constraint here, and then making this call P of n, and then we will be exploring this base case where n is going to be 0, and then we continue with this other path in which n is going to be greater than 0, and therefore producing the call with this n1, which is n minus 1, and continuing with the base case of this path and so on. Now, with this symbolic execution, the idea is that we will be getting the different behaviors that we can basically produce with this program, or in other words, we can be generating different inputs that we can provide to this program so that we will be exploring different paths. So for instance, an input with n equals 0, or with n equal 1, n equal 2, and so on. But the problem is that this branch here is going to be infinite unless we figure out that we have to limit the number of task switches that are allowed in the same object. And it is important to note that the usual loop K is not going to be applicable here. It's not going to be able to detect new tasks because it only works locally and in loops or in recursive calls, but locally in the same task. Okay, so if we put this task switches per object limit to 3, then we will end this derivation at this point, and then we will be generating these 3 test cases only for this case in which n is less or equal than m. Of course, we will have later to consider the other case. Now about the actor number coverage criteria. Here the idea is to limit the total number of created actors during the execution by program point. Well, and to illustrate this, let me just change the program that we saw before with this slight change, in which we can see that now to compute the factorial, instead of generating a new task with this decremented argument, we are doing this but on a different object, newly created object. A is going to be the one receiving this new task. Therefore, we can observe that, I mean, the shape of the tree is going to be quite similar, but the difference is that now there is not going to be a number of task switches in the same actor, but instead we will be generating a number of actors. And an important point to note here is that it is important that we are not limiting globally the number of actors, because that will result in a very unfair coverage criterion. Instead, we are limiting the number of factors which are generated or generated by program point. So in this case, if we allow just 3 objects or actors per program point, then we will be allowing only 3 actors generated at this program point where do we have this new, and therefore this derivation will end here, and we will ensure this finiteness of this symbolic execution. Okay, now just let me conclude and outline some research lines for future work. So we have proposed necessary extensions to apply to the context of symbolic execution the state-of-the-art parcel order reduction techniques in the context of actor systems. And also we have formalized and proposed a framework for symbolic execution and test case generation of actors, including the above extensions and including the definition of novel termination and coverage criteria. Also, we have implemented and evaluated for the APS language in the APET test case generation tool, which is available at this website, and the experimental evaluation demonstrate the effectiveness of the proposed techniques. And for ongoing work, we plan to provide support for handling in an intelligent way synchronization primitives like active and passive weights. And of course, we'll have to study here the problem of deadlocks. And also on another dimension, we also plan to study the problem of detecting independent tasks by means of symbolic execution. And well, that's the end of the talk. Apologize for not making it possible to be there, and thanks a lot for your attention.